Okay, we're going to take a look at exponential growth and decay. Okay, so rabbit populations, this would be one example of something that grows exponentially, at least for some period of time, where, say, you start with 2 rabbits and they make baby rabbits, and then you have 10 rabbits, and then they make baby rabbits, and then you have 30 rabbits, and this population grows exponentially. It's not linear. As there are more rabbits, the rate of growth gets to be larger. So we say that the number of rabbits in the population increase at a rate that is proportional to the number of rabbits present, which might sound a little bit confusing when you read that statement, but what that's saying is if there are more rabbits, the rate of change, we can call that dp dt, gets larger. This is true for really any population, at least for some period of time, that the population will grow exponentially until there's some limiting factors. And here's how we show that something grows at a rate that's proportional to the amount present. So dy dt, the rate of change of y with respect to time, is equal to k, a constant, times y, which is the quantity. So if y gets bigger, dy dt is bigger. Now we can solve this. This is a separable differential equation. Divide both sides by y, multiply by dt, integrate both sides. When we take the antiderivative of 1 over y, we get natural log of absolute value of y. We've got to be really careful of those absolute values there because we can't take the natural log of a negative. All right, if we want to try to isolate y, we can exponentiate both sides. That'll cancel the natural log. And e to the power of kt plus c is the same as e to the c times e to the kt. And e to the power of a constant is still just a constant. We drop the absolute value, make this plus or minus. But whether it's positive or negative, e to the power of c is just a constant. So we're just going to call plus or minus e to the power of c, we'll call that a. All right, if we look at what happens when time is 0, that's y sub 0, the initial y value. Well, e to the power of 0 is just 1, so that constant a turns out to be y sub 0, the initial y value. So we could be a little more specific with this equation, write this as y equals y sub 0 e to the kt. So if we're given a differential equation dy dt equals k times y, the solution is y equals y sub 0 e to the kt. That's our exponential growth equation. All right, so to summarize, if the rate of change is proportional to the amount present, then we have exponential growth. This is represented by the exponential change differential equation, dy dt equals k times y. So if you ever see that differential equation, you know that it represents exponential change. And this, when solved, produces the exponential change formula, y equals y sub 0 e to the kt. And if that constant k is positive, the equation represents growth. If that constant k is negative, the equation represents decay. All right, so let's look at compounded interest. You guys have seen in the past this formula here for interest that's compounded at some rate, some number of times per year. Well, it turns out if the best we can do with compounded interest is to compound continuously. If we do that, if we compound continuously, we take the limit as n goes to infinity, so we compound an infinite number of times per year. Now, unfortunately, we don't know how to do this yet. We'll learn this later in the year. For now, we can trust our calculator. You could plug this limit in, and we will get a equals a sub 0 e to the rt. So that's exponential growth. And you might see this written as a equals p e to the rt, p equals a sub 0. It's just a different notation. You've probably seen radioactive decay before. If you have a radioactive element, it decays at a rate proportional to the amount present. So we can write this equation as y equals y sub 0 e to the negative kt, which allows us to view k as a positive, but it's important to just understand that for decay, we should have a negative exponent. The half-life is how long it takes for half the material to decay. So let's take a look at an example here. We have our decay constant for some material that's decaying exponentially. So y equals y sub 0 e to the negative 0.013 t. If we're looking for the half-life, we're looking for half of what we started with initially. So 1/2 of y sub 0. And now we can cancel out y sub 0, and we can solve for t. Take the natural log of both sides, divide by negative 0.013, and we find that that would take 53.319 years. Application of exponential decay is Newton's law of cooling. If you leave some cup of hot coffee out in the open, it's going to cool down to room temperature, and it's going to cool down at the rate of negative k times the difference between the temperature of the material in the cup minus the temperature of the surrounding room. And if we solve that differential equation, we would get this formula right here for the temperature of the liquid. The good news is we do not need to memorize this formula. If it's ever needed, it'll be given to us, but we should be able to recognize it and solve for unknown variables. And you'll see some examples of this in the homework.